Hi. So you want a simple guide to the theory of relativity? Great, you've come to the right place. Part 1. Classical relativity. Let's start with some absolutes that we need to accept. 1. There is no such thing as absolute motion or absolute rest. Objects move relative to each other. For example, look at the truck with two kids playing catch. The truck is moving at a constant speed of 50 miles per hour, but as the kids are also moving with it at 50 miles per hour, they could easily think that they are standing still. When the children throw the ball at 10 miles per hour, they observe that the ball they have thrown is moving at 10 miles per hour. But their little brother, who is not on the truck and is standing still, has observed that the ball has moved at 60 miles per hour. He has added both the speed of the truck and the speed of the ball together. But is the little brother really standing still? No. The Earth is constantly in motion, the Sun is constantly in motion, and the galaxy is constantly in motion. Therefore, nothing is ever at absolute rest or absolute motion. Things just move relative to each other. This is classical relativity. Part 2. Special theory of relativity. Time dilation. The second thing we need to accept is that the speed of light is the same for all observers. So, let's imagine a beam of light being reflected between two mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors, but this time the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that the beam of light is moving a greater distance. Now, let's put a couple of people into this scenario. Meet Alex. He sits inside the moving set of mirrors, and Bill sits inside the stationary set of mirrors. The speed of light must be the same for both Alex and Bill, and their light beams must hit the bottom mirror after the same amount of time has passed. But as Alex's light beam is covering a longer distance, how is that possible? Well, the only way for that to work is if time for Alex slows down. Look at the clock hand. Notice how Alex's clock hand is moving much more slowly compared to Bill's. Time for Alex has slowed, which allows his light beam to travel a greater distance. Look at it this way. Speed equals distance divided by time. As Alex's distance is more, the value of his time must be more, or rather Alex's 1 minute actually turns out to be longer than Bill's 1 minute when you compare the two. Time has slowed down for Alex. This is called time dilation. This is quite a hard concept to grasp because it seems to go against what we experience on a practical level. But to understand the theory of relativity, you must stop thinking of time as a fixed unit for everyone. Time is relative. Confused? Don't worry if you don't grasp all of this immediately. Remember, it was the most brilliant scientist of the 20th century who put forward this theory, so feel free to rewatch this part of the video as many times as you need. Part 3. Special theory of relativity. Length contraction. In the previous section, we spoke about how the speed of light remains the same for Alex and Bill because while the distance Alex's light beam travels is more, his time has dilated. However, distance and time don't increase by the exact same amount. In fact, time doesn't actually dilate enough to account for the speed to remain the same for both boys. Something else happens: length contraction. When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So in this scenario, Alex and his mirrors are actually smaller than we thought, and therefore the distance the light beam has to travel is actually smaller than we thought also. In conclusion, time dilation and length contraction work together to ensure that the speed of light remains the same for both Alex and Bill. Einstein preferred to think of space and time not as two separate things, but one entity. He called it space-time. Part 4. Time travel. Time slows down for objects travelling close to the speed of light, and time stops altogether for objects travelling at the speed of light. It then follows that time must go backwards if objects travel faster than the speed of light. So far, it has been seen that no object can travel at the speed of light. On approaching the speed of light, objects start to increase in mass rather than speed, and it would take an infinite amount of energy for an object to achieve the speed of light. This is why we cannot travel back in time. We simply have not been able to reach a greater speed than the speed of light. Part 5. General Theory of Relativity. Einstein realized that the special theory of relativity, which we explained previously, only worked for circumstances when things moved at constant speeds through the universe. What about when objects sped up? What about the effect of gravity? And come to think of it, what is gravitational pull after all? Einstein theorized that objects warped space-time around it, causing it to become curved, and as a result, objects experienced gravitational attraction to each other. This warping of space-time explains how objects behave as they move through space. This is the general theory of relativity. Part 6. How do we know it's true? How do we know that the theory of relativity is true? Well, countless experiments have been carried out, and Einstein's equations hold true. Modern GPS uses Einstein's theory of relativity to pinpoint our locations with impressive accuracy. In 1971, an experiment was conducted with 4 super-accurate atomic clocks, which were set to the exact same time as a reference clock. The clocks were placed aboard commercial flights, and the planes flew twice around the world, first eastward and then westward. When the clocks returned and were compared to the reference clock, the clocks were no longer all synchronized, and the differences were consistent with the predictions of special and general relativity. So, that concludes our explanation of the theory of relativity. Bear in mind this is a very simplified explanation, but it should give you a basic understanding of the core ideas so you can study further on your own. We hope you enjoyed this video, and be sure to subscribe to London City Girl to see other interesting videos.